Hey, calculus. So you know a lot about derivatives and limits, and we're now going to talk about higher derivatives. And higher derivatives have great applications. So um, normally by this time we would have spent a lot of time on application and word problems, that type of business. We've kind of cut that out, but there is a we kind of introduce it now at this point. And the nice thing is that you get to use your notes as you kind of work through. Uh, but higher derivatives that they do again have a lot of application. And so if the original function is f, then the first derivative we just write is f prime. Second derivative, we put 2 tick marks. Third derivative, we put 3 tick marks. And that fourth derivative, you just start writing 4 and 5 in parentheses to let them know, let the person know that it's a higher level derivative. After a while, the tick marks kind of run together. People 1, 2, 3, 4, and then you put the line through. We have all sorts of ways that we use, um, kind of notation to make sense of numbers as we gather them. So what we want to do is we want to look at this, and there are 1, 2, 3, 4. 1, 2, 3, 4. There's five functions. So I think we're looking for f and f prime, f double prime, f triple prime, and f quadruple prime. I think that's what we're looking for here. And the question is, really starts with, well, which one is the original function? And suppose you just kind of start by picking one. It's really tough, to answer these questions. But suppose you say, well, I think that the green one is the original function. So let's say that that was f. Then what would its derivative be? Well, what do you know about the slope of f? The slope of f is always negative. So its graph would have to be below the x-axis the entire time. So that would make this one f double prime. Well, if that's f double prime, what can you tell me about the slope of or that would be f prime, excuse me. So if that's f prime, what can you tell me about the slope of that graph? Well, you can tell me that the slope is always positive. So f double prime is positive, which means it always sits above the x-axis. So, it looks like it would be the purple one. So the purple one would be f double prime. But then when you ask about the purple one, again, you're back to that situation like, well, the derivative is always negative. So I'd always be below the x-axis. So I'm back to the yellow one, but I've already used that one up. Sometimes it's good to just pick one and start with it and realize that, sometimes overlap. But what I like to do is this. I like to look at this piece. I like to look at where things cross the x-axis and where derivatives are 0. So that one, the blue one crosses the x-axis there. And the red one crosses the x-axis there. Okay? And the blue one has a derivative equal to 0 right there. So when I look at this graph, it appears to me that the blue one could be the original, and then the red one could be the derivative. Because you can see this red spot right there, it crosses the x-axis right when the derivative is equal to 0. Also, I want you to consider this. Look at the blue graph. Here, the derivative is negative, and the red graph sits below the x-axis. And then here, the derivative is positive, and the red graph sits above the x-axis. So I think that the red graph is an excellent derivative for the blue graph. So I'm going to try that. I'm going to say that's f, and I'm going to say that the red one is f prime. Well, if the red one is f prime, then let's talk about that derivative. The derivative of f prime, the derivative of the red, is always positive. So f double prime is always positive. So that means it's going to be above the x-axis. So I've either got the green one or the purple one. Which one is it going to be, the green one or the purple one? Well, if you look at that red graph, and you were to go to this point right here, say 1, 1, you could say let's graph it. It looks like the slope is about 1. Okay? So at 1, the purple graph has a value of, say, 2, whereas the green graph has a value of 1. So the green graph is a much better description of that derivative. So the derivative of the red graph is going to be the green graph right here. So that's f double prime. What can you tell me about the derivative of f double prime, or in other words, f triple prime? Well, it's always going to be negative because you can see that it's headed down. So this guy, the yellow one, is going to be f triple prime. What can you tell me about the derivative of f triple prime? Well, it's always positive. So the purple one is going to be f quadruple prime. So looking at graphs and determining derivatives, it's a little bit challenging. Don't feel like it's supposed to be easy. We'll kind of fight our way through it to some degree. But that's a graphical representation. The algebraic representation really isn't any big deal. Let's find the first and second derivatives of the functions. F prime of x is, you know how to do this derivative, 4x cubed minus 8x plus 2. And so the second derivative is going to be 12x squared minus 8. Look at the next one, f prime of x. Uh-oh, this tells me I need to use the good old chain rule. So I have u to the 5th, I have 2x minus 3, 5u to the 4th, and 2. We multiply those together, and you get 10 times 2x minus 3 to the 4th. Find the second derivative. Hey, got to use the chain rule again. I'm going to do it without the boxes. The derivative of the inside is 2. The derivative of the outside is 40 times u to the 3rd. So 80 times 2x minus 3 cubed. Look at that. We're going to do 2 more that are a little bit trickier. We're going to get rid of d. I like d, but we don't need to do it this year. F prime of x. Notice that when we take this derivative, it requires us to use the chain rule. I have u to the 1/2, and I have 2x minus 3. The derivative of u to the 1/2 is 1 over 2 roots of u. And the derivative of 2x minus 3 is 2. As you multiply, the 1/2 and the 2 go away, and you get 1 over root of 2x minus 3. Now let's set up our second derivative. As we set up the second derivative, I'm going to rewrite the first derivative as 2x minus 3 to the negative 1/2 power. So as my writing as a negative power allows you to use the chain rule. Otherwise, you have to use the quotient rule, and I don't like the quotient rule. I wouldn't say I don't like it. That was probably a strong statement. Sorry, quotient rule. Just I don't like you as much as the chain rule. Chain rule is so beautiful. Okay. Derivative of u to the negative 1/2 be negative 1/2 u to the negative 3/2. So u to the 3/2 in the denominator. Derivative is dos, which is Spanish for 2. And when I multiply, the 1/2 and the 2 go away, I get negative 1 over 2x minus 3 raised to the 3/2 power. Yeah. Sometimes people wonder, how do you check your answers? Again, just great mathematicians, they always know how to check their answers. It's always a way to check your answer. Always, 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 always. Look at that first function, square root of 2x minus 3. And when you look at that graph, you say, well, there's a graph that is, the slope is always positive. So its derivative should always be above the x-axis. Well, go ahead and graph the derivative. See if it matches up. 1 divided by, parentheses, square root of 2x minus 3. Check out that graph. Is it always above the x-axis? It sure is. You can see it levels off, that the slope gets really, really down there. I'm going to go to my window here because I don't like it. I'm going to go y minimum -4. I'm going to go to +4. Check that guy again. Try to get just a little bit better picture there. Yeah. And then what would you say about the derivative of that graph? You would say that it's always negative, so it should always be below the x-axis. Let's look at one more. We'll go look at -1 divided by parentheses 2x minus 3 raised to the parentheses 3/2 power. And when I do that, there it is. So what a great way to confirm that your answer is correct. It's by looking at that graph. The last one. We find the first and second derivatives. This one involves implicit differentiation. The derivative of 9x squared is 18x. The derivative of y squared is 2y, y prime. And the derivative of 4 is 0. As I subtract the 18x, I get 2y, y prime is equal to -18x. Divide by 2y of y prime is equal to -18x over 2y. Or y prime is equal to -9x over y. That's y prime. What I would like to do now is I would like to find y double prime. Notice as I find y double prime, I have the quotient rule. I start with the derivative of the top, -9 times the bottom, y, minus the top. Well, that would be -9x, so plus 9x, times the derivative of the bottom, y prime, divided by the bottom squared. Now that all looks fine and dandy, except for one thing. We can't leave this y prime there. We must substitute x and y back in. And so, in this situation, we arrive to y double prime is equal to -9y, I'm going to write this over 1, plus 9x, I'm going to write that over 1, times -9x over y, all over y squared. I now have a complex fraction. Y double prime is equal to -9y over 1 minus 81x squared over y, all over y squared. Multiply the top and bottom by y in order to find common denominators. And I get y double prime is -9y squared minus 81x squared over y. I divide that by y squared over 1. When we divide by y squared over 1, we multiply by the reciprocal. I get y double prime is equal to -9y squared minus 81x squared over y cubed. And at this point, you are saying, yay, I got that done. But this can actually be simplified. And I know you might fight it. But just trust me, it's so pretty. I'm going to factor out a -9. And when I do, I'm left with 9x squared and a positive y squared. And even at this point, you're saying, okay, fine, Mr. Guest, we factor out that negative. Are we done? And I say, folks, there's something that's staring you right in the face. It's that guy. 9x squared plus y squared. What is that? Follow me. We've seen it before. It's right there. It's 4. And so therefore, when you multiply that by 4, y double prime is negative 36 over y cubed. That, my friends, is the answer. That's pretty. That's beautiful. Soak it up. Good times, good stuff. Get ready for the word problems. We'll see you soon.